Okay, let's go ahead and work on this problem. So I'm sure most of you recognize a problem. This is similar to a homework problem where you have to use the limit definition of the derivative to find the partial derivative. So this actually is how you define the first part, the partial with respect to x, right? It's you're having a small change in the x and you're seeing what happens to the function as you have a small change in x. So we're going to simplify this. It's really just like we did back in 17a with the limit definition. We're going to expand this out. We're going to get the limit as h goes to 0. X plus h squared is x squared plus 2xh plus h squared times y cubed minus 5x squared y cubed. All divided by h still. And then, oh, that's not h, that's... And the way I would look at this first part is it's 5y cubed distributed to each of these things. So it's 5y cubed times x squared. So I'm going to get the limit as h goes to 0 of 5x squared y cubed. And then 5y cubed times 2xh is going to be 10x h y cubed. And then 5y cubed times h squared is going to be 5h squared y cubed minus 5x squared y cubed all over h. And then just like in 17a when we did the limit definition, the things that don't have h's cancel out. Everything that's left does have an h. You can factor an h out, cancel with one at the bottom. So I'm going to erase this because we have this over here already. So factoring out an h from the top, I've got the limit as h goes to 0 of, let's see, h times 10xy cubed, and then 5hy cubed. Divided by h. These h's cancel, and then I take the limit as h goes to 0 of 10x cubed y plus 5hy cubed. By the way, for the homework problem that you have to do, this is what they want you to put into the first part of that problem, where you're taking the limit as h goes to 0 and you have to simplify as much as possible. This, for the one I've done, is the most simplified version. That's gosh, the words are challenging right now. It's the most simplified version of this expression before you take the limit. So then we take the limit as h goes to 0. So this h goes to 0, and you get 10x cubed y, which is the partial derivative of this function with respect to the variable x. Again, an easier way, so a way to do it without using limit definition is to look at this function, treat y or y cubed like a constant, and differentiate this. So in fact, let's go ahead and find, before I start erasing willy-nilly here, I don't want to erase right away because it's kind of fast. But let me just go to the other side. Hope you guys all had a nice weekend, a nice Easter, if you celebrate that sort of thing. It was also my brother's birthday on Easter this year. He turned 39 yesterday. It's interesting, I was looking at the calendar, like Easter, the day of the month it happens on really kind of varies a lot, as I'm sure you know. But some days happen more frequently than others. Apparently, like April 19th is the most frequent day that Easter occurs on in the last like 1,000 years or something, or 600 years. Kind of like 3.8% of the time or something. Anyway, that's what that kind of stuff I think about on Easter. How often is Easter on this day? Okay, so for this function, 5x squared y cubed. Now we're just going to find all of the first and second partials. So we're going to find the partial with respect to x, which we already did. Again, when I'm looking at this and I'm saying I'm going to differentiate with respect to x, I'm really thinking of this as the constant 5y cubed times x squared. When I differentiate that, I get 5y cubed times 2x, which I would then write as 10xy cubed. My first partial with respect to y, Well, again, I'm going to think of this now as a constant times y cubed. In fact, it's already kind of written that way. Here's my constant, 5x squared. Here's my variable, y cubed. The derivative is going to be the constant hangs out, and the derivative of y cubed is 3y squared. So that's going to be 15x squared y squared. Let's find fxx and fyy. Fxx, the second partial with respect to x. Well, again, we're going to do the same thing. I'm going to think of this. I don't think I really need to rewrite it. I can see that that's going to be the constant 10y cubed. I'll rewrite it anyway, just for fun. This is 10y cubed times x. And if I'm differentiating with respect to x, y is a constant. So this constant multiple hangs out, and the derivative of x is 1. So that would be 10y cubed. And not that I asked it, but just to point out, if you went one more partial with respect to x, if you did fxxx, took the next derivative with respect to x, you would get 0, because there's no x's left here. So this is just a constant, and the derivative of just a constant that's not multiplied by a variable is 0. Let's find fyy. Fyy, so again, this is my constant multiple of y squared. The derivative is going to be 15x squared times the derivative of that, which is 2y, which is 30x squared y. You don't need to show these intermediate steps. Like, it's totally fine. So you go from like, oh yeah, the derivative of y squared is 2y, so I'm going to get 30x squared y. I'm just trying to show you the steps so you can really see what's happening here. Let's look at the mixed partials, which again, we can count on always being the same. So both fxy and fyx. So fxy, I'm going to write it this way just so everyone can see it. It's first the derivative with respect to x. So that's 10xy cubed. And then I'm differentiating that with respect to y. So there's the symbol I'm going to use for that. The partial derivative with respect to y, del y, of 10xy cubed, which is my fx. So I did the derivative with respect to x first. Now I'm doing the derivative with respect to y second. So let's see. The derivative of 10xy cubed is going to be 10x times 3y squared, which is 30xy squared. I think I can squeeze in fyx, which should be the same. So fyx is going to be del x, right? So we're doing the derivative with respect to x second of fy, which is 15x squared y squared. All right, we're differentiating that with respect to x. We did y first, we're doing x second. The derivative with respect to x is going to be 30xy squared. And to no one's surprise, those are the same, which they should be. Again, I will just briefly mention, hopefully this is the last time I'll say it. There are some very weird functions that are kind of specifically designed where these aren't the same. But we're not going to encounter those in this class, so you shouldn't worry about them. Yeah. All right, let's back up a step, because I know some people had some questions about specifically the second quiz, quiz question number 2. I will post the solutions of the quiz, by the way. I've written them up, I just haven't gotten to posting them yet. Hopefully I know I typed them all up last quarter. These ones I might have to write stuff with my own hands because some of the things I'm less good at typing up. So I wrote these up, and hopefully we can read them when I post them. If you have questions about anything I post quiz solution wise, just shoot me a message and I will happily clarify anything. But people had questions about which one was it here? Let me take a look. Number 2, which is this one. F of xy equal to 1 over the square root of x squared plus y squared minus 1. And in part C of the previous question, we were already asked about the domain and the range. So let's just go ahead and cover that because it's worthwhile. So the domain here, we're setting, so usually, actually this is a really good question because it kind of incorporates 2 things. Usually we would just say, I want x squared plus y squared minus 1 to be greater than or equal to 0. because it's the stuff that's inside the square root. But in this particular case, if this was equal to 0, the square root of 0 is 0, and then you'd be dividing by 0. So in this case, we actually also want to exclude 0. You could write this, you could say, I want this to be true, and I also want the denominator, right? I want to exclude where the denominator is equal to 0, which is just the same as saying, well, I don't want the insides to equal 0 because the only way the square root equal to 0 is if the insides are equal to 0. So instead of writing all that, let's just say it's going to be greater than 0. So again, usually the insides of a square root are greater than or equal to 0. But in this case, since it's in the denominator, we don't want 0 either. All right, so I would add 1 to those sides. And then I would think about, well, I know that the circle, I know that the equation x squared plus y squared equal to 1 is a circle of radius 1, centered at the origin. I should say most of the circles that we encounter in these domain and range problems are almost always centered at the origin. You could have something different, but it's usually we kind of limit it. So here's what my domain looks like. Got a circle of radius 1. Do I want to include the boundary or not? That's a good question. What do you guys think? Do I want to include points on the circle? So let me ask you guys, yes or no? You can use the reactions. So right, there's this little reaction button down here. You can click a green for yes or a red for no. And I will actually look at what you guys are doing for a second. So I didn't ask the question yet. Oh, I guess I did ask the question. Do I want to include points on the boundary? So like, do I want to include the point 0, 1? Yes or no? Yeah, I see of the people who are answering, I appreciate it. I see mostly no's, and it's true. It is definitely no, because if you include the point 0, 1, for example, if you plug that in, 0 squared plus 1 squared is equal to 1, and that's not greater than 1. Right? It would be fine if this wasn't in the denominator, but it is. So if you plug in 0, 1, you're going to get division by 0. Let me stop being in the gallery view here, so I can. Right, so the video later doesn't look weird. If we're asked to draw the domain, that means we need to draw the boundary as a dashed circle. We still have to ask ourselves, do we want the stuff that's inside the circle or outside the circle? So I usually test a point. I usually test the origin. If I test the origin 0, 0, 0 squared plus 0 squared is 0, and 0 is greater than 1, it is definitely not, right? That is not true. So we don't get the point 0, 0. So we don't get any of the points that are inside the circle. So our domain here looks like everything is outside the circle of radius 1. That's our domain. Neat. The range, again, the range is a little bit more challenging. So I've been kind of doing this thing with the range where I kind of take my equation and manipulate it. I'm going to kind of talk about this in 2 different ways. So you guys can think about this in all the ways. I'm going to erase the picture of the domain because I think everyone saw the picture. There it is. It's everything outside the circle, not including the boundary. Now I want to talk about the range. I'm going to talk about the range firstly in more of just a common sense kind of way. So when I talk about the range, I'm usually trying to think about 2 questions. If it's some things require a little bit more detailed analysis, but most of these we can kind of just ask these 2 questions. How big does f of x get, and how small? Okay, let's talk about how small first, for no particular reason. So let's see. Could I make the, so in this one, there's kind of an added question. It's a fraction. And the other part of the fraction that's actually changing is the denominator, right? The numerator is going to be always 1. So in this fraction, if I want to make the fraction small, to make a fraction small, we want to make the denominator big. How big can I make this denominator? I can make it as big as I want, right? Y could be 1, for example, and x could be infinitely large, right? X would just get bigger and bigger and bigger and bigger and bigger. So I can make this whole fraction smaller and smaller and smaller. Do I want it to equal 1/2? Sure. I let y equal 1 and x equal 2. In fact, I can get any fraction. So pick any fraction you want. I'll pick an easy one. Like say I wanted, I don't know, 1/1000th. I could let y equal 1 and x equal 1000. Or even x would be negative 1000. Right? Because if y is 1, then 1 minus 1 is 0. And if x is 1000, the square root of 1000 squared is just 1000. So I get 1 over 1000. So I can make this as small as I want as long as it's positive, right? But this can never actually be negative because the square root's always a positive output. And it can never be 0 because 1 on top, right? A fraction can only be 0 if you can make the numerator equal to 0. I still have a big old no on my screen here. Let me close my no. Can I? All right, sorry, I have to click on the reactions. Now I'm not knowing enough anymore. Okay, so we can say this can be as small as almost 0. Right? We can get any positive number, but not 0. So what I would say is the function f of xy is certainly going to be greater than 0. You can get any value that's greater than 0, even super small ones. Okay, let's talk about how big it can be. So to make the fraction big, we're going to make the denominator small. Okay, well, how small can we make the denominator? Well, it can't be negative, but could it be 0? Well, okay, so could it be 0? No, not technically, right? You can't. Well, it can actually be smaller than 1 max. So we can make, for example, you could let, I'm going to pick these numbers again. I'm going to pick x equal to 1, and I'm going to pick y equal to something super duper small. Y is going to be, I don't know, 1/1000th. Then if I plug those numbers in, here's what I get. I get 1 over the square root of 1 squared plus 1/1000th squared minus 1. The 1 squared minus 1 cancels. And then you get 1 over, well, the square root of 1/1000th squared is 1/1000th. And 1 divided by 1/1000th is 1000. But here's the thing. I can set x equal to 1, and I can make y any small number I want. 1/1,000,000th, 1/1,000,000,000th, 1/1,000,000,000,000th, which is going to make this equal to those big numbers, billion, trillion, etc. So the whole thing here is I can see that if I hold x equal to 1 and let y go really, really close to 0, this whole fraction is going to get super duper big. Or what I should have said maybe is that if you can let the denominator go to 0, right, we can definitely get the denominator closer and closer and closer and closer to 0. That means the fraction is going to get larger and larger and larger. It's going to get infinitely large. So this is kind of the more common sense talking it out way. Like you say, you ask yourself, how small can I make my expression? How large can I make my expression? And it works kind of depending on how good you are at saying those things to yourself and really kind of answering those questions. A more kind of methodical way of doing it would be the following. So we can look at, we know that we have this condition. We know that x squared plus y squared minus 1 because of the domain. So when I'm asking about range, I'm usually starting with what my domain tells me. My domain was that x squared plus y squared minus 1 is less than 0. Now, sometimes, depending on what you're working on, you'll have some sort of upper limit as well. In this case, we don't. Right? X squared plus y squared minus 1 can be as big as infinity. I mean, as big as any big number, right? It can't actually equal infinity, not a real number. Okay. So, but this can get infinitely large. So then what I'm going to do is I'm going to take this expression in the middle and try and make it look like my function. My function, which was, what was my function? It was 1 over the square root of x squared plus y squared minus 1. So first I'm going to take the square root of everything. So the square root of 0 is less than the square root of x squared plus y squared minus 1 is less than the square root of infinity. But the square root of 0 is just 0. And the square root of infinity is just infinity. And then we're going to take the reciprocal of everything. Now, when you take the reciprocal of everything, it changes the direction of the inequality. Right? If you're a number that's bigger than 0, then your reciprocal is going to be smaller than the reciprocal of 0, which is infinity. Oops, so I take the reciprocal of everything. So 1 over 0 is bigger than 1 over the square root of x squared plus y squared plus 1, minus 1, sorry, is bigger than 1 over infinity. The 1 over 0 really, right, that's getting infinitely large. And 1 over infinity, that's getting infinitesimally small. So look, we actually, right, doing this didn't actually really change anything, but it still is important to do. So here we see, oh yeah, look, my 1 over the square root of x squared plus y squared minus 1 is bigger than 0, but is less than infinity. So my range here is 0 exclusive to infinity exclusive. Great. Someone asked me this question before, and I think it was a really good, not in class, but like in their reflection. They asked me the question, are the level curve values and the range values always the same? And the answer is yes, right? So if we're going to do the next part, we're going to do part 2 of the question, right? Or we're going to do question 2, which is how to use this function, to draw some level curves here. The only values I can pick for level curves are values in this range from 0 to infinity. Let's go back and look. So this is my function, right? I definitely cannot pick a level curve value like z star equal to 0 or z star equal to any negative number, right? I can't pick these because if I set this function equal to that, there's no solution. Another way to think about it is if you graph this surface, it doesn't go that low. You're never going to, it's kind of like if I said my function is y equal to 1 over x, and I want to see what happens when I set, y equal to 0. Well, if I set y equal to 0, I get no solution, right? This doesn't have a solution. I suppose let me make x squared to make it a little more interesting. If I set y equal to -4, right, this has no solution. Because if you look at the graph of 1 over x squared, it looks like this. Right? It never gets to y equals 0. It never gets to y equals -4. There are no graph values that hit those values. So it's the same idea here, right? Just like the range of this function, 1 over x squared, is also 0 to infinity. That means you can't have any places where it's equal to something that's not in the range. So level curves are values that the function's equal to. They have to be in the range. It's a good question, right? It's one that definitely makes us think about what are we really saying with all of this? So I want to, what is that? I want to graph the level curves. Okay, so I think the best way to do this, if I'm trying to graph the level curves, is I'm going to set this equal, I'm going to set z star, he likes to use z star, let's use z star. Z star equal to 1 over the square root of x squared plus y squared minus 1. And we're going to try and, there's usually one of two things you want to do. Either you want to solve, let's just say isolate. Either you want to isolate y as a function of x. I suppose also x as a function of y would be also not bad, or x as a function of y. Right, like for example, if you got x equal to y squared plus 1, you would probably actually want to think of graphing it that way, which would look like this. Right, it's a rightward opening parabola with an intercept of 1, 0. It's much easier to deal with that than it is to solve for y and say y squared equals x minus 1 y equals plus or minus the square root of x minus 1, right? That's just not, it's not as helpful. So one of those two things, or the other thing that comes up usually, like in this example, is you want to isolate x squared plus y squared. If you have an x squared plus y squared, that's usually where we're going. I should say, if you have an x squared plus y squared and no other instances of x and y. All right, so let's go ahead and multiply both sides by its denominator. So the square root of x squared plus y squared minus 1 times z star is equal to 1. Let's divide both sides by z star. Let's just do that right now. I suppose another way you could have done this would have been to just take the reciprocal of both sides and say 1 over z star equals the square root of x squared plus y squared minus 1. And then we're going to square both sides. So x squared plus y squared minus 1 equal to this thing squared, which is 1 squared, or 1, over z star squared. And then finally add 1 to both sides. So that x squared plus y squared equals 1 plus 1 over z star squared. And now we can actually use this to classify or think about what our level curves look like. No matter what the value of z is, notice, right, z can't be 0. It is true that in this equation, it looks like it would be okay for z to be negative, but we know z can't be negative because it's not in the range of our function. But this definitely looks like a circle centered at the origin. And the radius is the square root of what's over here, right? If you had x squared plus y squared equal to 9, the radius would be the square root of 9, which is 3. If x squared plus y squared equal to 1 plus 1 over z star squared, your radius is the square root of 1 plus 1 over z star squared, whatever that number is. So then we do the thing. So I think our specific values were z star equal to 1/10, 1/2, 1, 2, and 3. So the reason we did that work is so we don't have to do it again, right? For 1/10, I know it's centered at 0, 0. I know my radius is the square root of 1 plus 1 over 1/10 squared, right? Let me write that in here. The radius is the square root of 1 plus 1 over z star squared. And that's why we do that. So then we can just say, oh, if I plug in different values of z star, I can easily think of what my level curve or my contour looks like. So this is going to be the square root of 1 plus 1 over 1/100th is 100. So that's the square root of 101, which is just slightly bigger than 10. If we do 1/2, which I'm kind of going to leave myself more room here. So for 1/2, we get r equal to the square root of 1 plus 1 over 1/2 squared. 1 over 1/4 is 4. 1 plus 4 is 5. So radius is the square root of 5. For 1, sorry, I'm like trying to make this look not terrible. It looks terrible. For 1, you get r equal to the square root of 1 plus 1 over 1 squared, which is the square root of 2. For 2, you get r equal to the square root of 1 plus 1 over 2 squared, which is the square root of 5 over 4. And then finally for 3, so I'm trying to say a different like graph the thing. For r equal to 3, you get the square root of 1 plus 1 over 3 squared. So 1 plus 1/9, which is the square root of 10 over 9. Notice that no matter what value we pick for z, you're always going to get 1 plus something in your square root. It might be something big if z is small. It might be something small if z is big. But no matter what we're getting, it's always 1 plus a little bit more. Which means our radius is always going to be just a little bit bigger than 1 if our inputs are really big. Which again makes sense because we know that our domain, right, is everything outside of the circle of radius 1. Let me make sure I'm saying that right. Yeah, that's right. Right, we can't get the circle of radius 1 as a level curve, right? Sorry, I'm trying to make sure that's, yeah, right. Yeah, totally. Yeah. You're outside of that circle. So let's try and draw this. It's going to be a little bit dicey here. So yeah. So here is z star equal to 1/10. So let's say like 10 is right there. And here's our, so when you're drawing these level curves, you need to draw the curve, and then you also have to label it. And this is z star equal to 1/10. And then for 1/2, let's use a different color. So for 1/2, the radius was square root of 5, which is a little bit bigger than 2. I'm gonna try and make my 1 and my 2 a little bit exaggerated because they're gonna get kind of squished in here. In fact, actually, let me make this less of a lot of room here. So for the square root of 5, that's like 2.3-ish, I think. 2.2. I don't actually know. But let's say it's about right here. I know that's way not to scale. It's all right. So here's, I mean, it's kind of all right. So here's z star equal to 1/2. Maybe I should just move my 10 further out, but I'll go further. And then for z star equal to 1, the radius is the square root of 2, which is like 1.4. And this circle is not the best circle. And so that's right, that's z star equal to 1. And for z star equal to 2, we have the square root of 5/4, which is like, I don't know, 1 point something. And then it gets hard to label it, but there's my z star equal to 2. And then finally, the last one that we were asked to graph, here's my z star equal to 3, which still has a radius bigger than 1. So again, right, this picture, obviously not awesome. Let's actually, so that's how you draw it. Let's go ahead and look at Desmos real quick, just to kind of see how a little bit better, right? Yeah, I think it's worthwhile. So let me share. So we can graph this all without too much trouble, right? X squared plus y squared equal to, and let's just copy that before we write the other things. Let's be smart. Paste. So our equations were, let's see, well, actually, we didn't write that. The equations are on the other side here. I didn't write the equation. So my equation would be, right, the radius is the square root of 101. The radius would be that it was equal to 101, or the equation would be equal to 101, right, because it's the square of your radius. And then for 1/2, it would be equal to 5, because your radius is the square root of 5. And then for 1, it'd be 2, because it's the square root of 2. And then for 2, it would be 5/4, because it's the square root of 5/4. And then for the last one would be 10/9. So that's what your level curves would look like. And you can see, right, as you get into closer to the middle, right, they get really, really close to each other. If we graph this using the 3D grapher, so here's what we should expect, right? From top to bottom, it's the smallest values of z to the largest values of z, right? Is that correct? Yeah. So we expect that, I'm sorry, you can't see the top anymore, right? So it looks like the higher up, the lower, these are the smallest values and these are the largest values. So the small values of z, so when we're way out, we're low. As we move into a smaller circle, we are higher up. Smaller circle, higher up, smaller circle, higher up. So we expect this, I'm expecting kind of like some sort of, what I'm really thinking of is the book, like the Dr. Seuss book, Oh, the Places You'll Go. I think there's like a really kind of, let me actually, now I'm like, oh, the places you will go. Yeah, right? This thing, that thing right there. I'm expecting a shape that looks like that. That is literally what I'm thinking of when I'm thinking of what this looks like. Let's go ahead and graph it using the 3D grapher. Let's use the GeoGebra one. I think the GeoGebra one is a little bit nicer, I gotta say. Let's check it out. Let's graph f of xy equal to 1 divided by the square root of, and hopefully that works for square root, x squared plus y squared minus 1. Yeah, cool. Can we move this thing around? Yeah, look at that. So it totally looks like that. That's pretty neat. I like the GeoGebra one because you always know, like, I think it always tells you which axis is which, or which is the positive direction. So like, I'm pretty sure X is red and green is Y. But anyway, so that's cool. It looks like what we kind of thought it would look like, right? As we go higher up, we get further in, sort of like way out. I mean, you saw the pictures. Looks like it. Yeah, it does kind of look tricky. Except, so here's what I should say, Connie. Yes, but this graph that they have shown us, right? This graph that we've done here is not the entire graph, right? You can never, I mean, for most things, you can't really ever have the entire graph because they kind of keep going forever. So this would keep going up and up and up and up and up and get more and more and more and more narrow. It would be like a tree trunk, except an infinite tree, because it would keep getting, well, I mean, I do like your thought though, Connie, because it actually does, right? Because the narrowest it can get is having a radius of 1. So it never has the same radius anywhere, but it does keep getting closer and closer and closer to having a circle of radius 1 as its diameter, I guess. So yeah, it's very, the more I say, the more I agree with your analysis. It is very tree trunky, but it does keep going forever and ever and ever. Okay, let's see. We got like 8 minutes left. I feel like there was something else important I wanted to say. Maybe not. Oh, someone asked me this one. Yeah, let's do that. So let's look at some more partial derivatives, because partial derivatives are definitely going to be a lot of what we're doing. I think I'll leave it more to Professor Lewis to, at least at this point, say the things about what a partial derivative really means. But generally, right, it's the rate of change of your function in a particular direction. So, right, if you're moving in the x direction, if x is real, you're asking how the function is changing as x is changing. Same thing if you're moving in the y direction. But we might ask a question like this. So someone asked me this one, and I'm going to change it up just a little bit to make it a little bit different. Let's say our function is sine of, sure, let's do x to the 5th minus, let me be not very interesting here. Sure. Yeah, why not? Minus 3y. And I want to find fy of, sure, 0, 2 pi. So first, before we even think about the 0 to pi part, let's just find fy, the partial with respect to y. So fy, so we're taking the derivative of this with respect to y. So again, two variables are 1. I'm still thinking of the chain rule. I'm still thinking I've got sine of some stuff, right? I don't care that it's x and y. I just know it's sine of something. And we all know, we should all know, the derivative sine of something is cosine of something. So the derivative sine of some stuff is cosine of your stuff times the derivative of your stuff. Right, that's what's going to happen. So now let's do those things. So cosine of my stuff, that's x to the 5th minus 3y. And then the derivative of my stuff is going to be, well, now is where we have to think about the partials. Right? The derivative of x to the 5th minus 3y, well, if I'm taking the derivative with respect to y, x is acting like a constant. The derivative of x to the 5th, since it's not multiplied by any y's, the derivative of that is just 0. The derivative of negative 3y is going to be minus 3. So our partial derivative with respect to y is going to be negative 3 times cosine of x to the 5th minus 3y. Now we can plug in the point there. Fy, the partial with respect to y evaluated 0 to pi is going to be, let's see, negative 3 times cosine of 0 to the 5th minus 3 times 2 pi. I should have picked pi. Oh well. So that's going to be negative 3 times cosine of negative 6 pi. Negative 6 pi, if you look at the unit circle, here's 0, and negative angles make you go clockwise. So there's negative 2 pi, again, negative 4 pi, again, negative 6 pi. It's 3 full revolutions in the opposite neutral direction. But we're still ending up at this point on the unit circle, which has coordinates 1, 0, which means cosine is going to equal 1. Though, yeah, good question, Max. So is the variable in the subscript the one you're keeping constant or the one you're differentiating with respect to? It's the one you're differentiating with respect to. So when I say fy, I'm taking the partial derivative with respect to y, which means I'm keeping every other variable constant, whether it's just x or whether there's many variables. For example, yeah, let's look at one more. I got all kinds of stuff. We can have functions of many variables, not just 2. Let's say I have the function f of x, y, u, v equal to, let's not make this too terrible. Let's make it x to the 4th y cubed plus u squared x cubed plus v to the 4th y to the 3rd plus, sure, I don't know. You're like, this is not too terrible. It is a little terrible. Let's do one more. Sine of x cubed. I've got too many x's. Let's do u cubed v. V squared. Okay. So let's say I want to take some of the derivative partials here. So let's say I want to find fx. So the derivative of x to the 4th y cubed is going to be 4x cubed y cubed. This part's the variable. This part's the constant multiple. Constant multiples hang out, and we take the derivative of the variable part. Same deal here. The u squared is going to hang out because it's multiplying a variable thing. The derivative of this is going to be 3x squared times u squared. The derivative of this is going to be 0 because there's no variables in there. The derivative of this also going to be 0. There's no variables there. Let's find fy. So now this part here, I'm going to get x to the 4th times 3y squared, which I'm going to write as 3x to the 4th y squared. Usually I write these alphabetically, which means I should have probably written this as 3u squared x squared, but I didn't. Derivative x squared u squared is going to, sorry, u squared x cubed is going to be 0 because there's none of the variable we're differentiating with respect to. Derivative v to the 4th y cubed is going to be v to the 4th times 3y squared, which I would probably write as 3v to the 4th times y squared. And the derivative sine of u cubed v cubed squared is going to be 0. Let's do fu. Ha ha ha. Didn't do that on purpose, but you know, sometimes it happens. Derivative x to the 4th y cubed is 0. Derivative u squared x cubed is 2u x cubed. I should say order of your variables doesn't actually matter. It's just we usually try to write them in alphabetical order, but it really doesn't matter. Derivative v to the 4th y cubed is 0 with respect to u. Derivative sine of u cubed v squared is going to be cosine of my stuff times the derivative of my stuff. And the derivative of u cubed v squared with respect to u is going to be 3u squared v squared. Let's find the last one. Might as well, right? We're this far. Fv, derivative of x to the 4th y cubed is going to be 0. Derivative of u squared x cubed is going to be 0. Derivative of v to the 4th y cubed is going to be 4v cubed y cubed. And the derivative sine of u cubed v squared is going to be cosine of my stuff times. So notice in both of these, when we did the derivative of this with respect to either u or v, you still get cosine of the same thing. Because you haven't differentiated it. Well, I mean, you have, but you only differentiated the sine part. And sine of a thing, the derivative is always cosine of the same thing. But then we have to multiply by the derivative of the insides, and here's where they're going to differ. With respect to u, the derivative of the inside was 3u squared times v squared. For the derivative of this with respect to v, it's going to be u cubed times 2v. All right.